Hi everyone, in this video I'm going to walk you through homework 4, most of which is about hypothesis test and confidence interval. So hypothesis test, as we discussed in class, is like you propose some speculation or a statistical parameter like the parameter for population mean, and then you collect some data and then try to evaluate the evidence and try to make a decision whether you should embrace the null hypothesis or reject the null hypothesis. And confidence interval, on the other hand, is an interval, and we are 95% confident that the true parameter will be living in that interval. On another note, we introduced a framework of hypothesis test and confidence interval, and we can apply them to both one population scenario and two population scenario. In one population scenario, it's usually about making inference about population mean, like whether mu equal to something, or try to generate a confidence interval for mu. And on the other hand, the two population scenario, we are always interested in compare mu1 and mu2. And in this video, I'm going to present to you two approaches to work on this kind of problem. One of them is, doing totally everything by hand, and the other is to do everything in R. So in a former way, although I said I will do everything by hand, but I will still use R as a calculator, and I recommend you to do the same thing. So without further ado, let's get started. Okay, the first question is about to find the standard error of the mean, which is pretty simple. You first have to find out the standard deviation of the sample and then divide it by the square root of the sample size. So as you can see here, this is our data set. And we can easily calculate the standard deviation by using the SD command. And we want to divide this standard deviation by the square root of the sample size. There are two ways to find out the sample size. First of all, you can just count how many observations you have. 1, 2, 3, 4, 5. Or the other way is to use the length function. So you can do something like this. As you can see here, the length of the weights is 5. So you can plug in this number and put it under the square root. And this is the standard error of this sample. Okay, the second part, we want to find out the 90% confidence interval for the population mean. So as we've talked about in class, actually all the confidence interval that we talked about follows the following format. It's always like the mean plus or minus some constants multiplied by the standard error of y bar. And in the first part of the question, we already figured out what the standard deviation of y bar is. Let's call it SE. And the mean is something that's quite easy to calculate. So the only question is how to find this, multiplier. Well, this is actually pretty simple as long as you can understand this graphic. We are dealing with 90% confidence interval, so that means we want to find a cutting point like A and B. So in this case, A and B cut this distribution into three parts, the 5% here and 5% here, and that makes it 90% in the middle. So actually we want to find A and B. Also, because this distribution is symmetric around 0, so actually it suffices as long as we find one of them because they are symmetric around 0. And by definition, actually, A is the lower 95 quantile of this distribution. In other words, 95 of the data would be smaller than A. So let's find this out. Here, A has to be the 95 quantile of T distribution with degree freedom 4. Well, how do I know it's 4? Because this is a one sample T test, so the degree freedom has to be the sample size minus 1. So in this case, the sample size is 5, so that's why the degree of freedom is 4. So this is the quantile, and this is the degree of freedom. So if you run this line of code, you will see that A equal to 2.13. So next thing is to plug everything from the template. So the first of all, the mean is the mean of this sample, and A, we already find it, it's this critical value, and multiplied by the standard error, which is something we've already found out from step 1. So let's run this line of code. The left boundary of this confidence interval is 23.4, and the right boundary can be simply given by changing this negative sign into a positive sign, and run this line of code is 40.04. As I said in the intro, I'm going to talk about two different approaches to solve this kind of problem. The first of which, of course, is doing everything by hand, and this is counted doing every quantity by hand because we know everything happened under the hood, and we only use this R as a simple calculator. You see, we are just doing standard error calculation and mean calculation with R, nothing fancier than that. However, we can use some built-in function in R and avoid all of this hassle. So that command is t.test. So what we have to do is just pass in the weights here, and of course because we are talking about a 90% confidence interval, so we have to specify that because the default value is 95% confidence interval. So conf level has to be 0.90. We will get the confidence interval which starts from 23.4 to 40.04, and let's compare this with what we just got. It is identical. Okay, in this question you're supposed to do a 95 confidence interval. So you can just follow what you did, everything exactly the same, except you have to change the confidence level accordingly. For instance, if you want to do everything in R, this is how you are supposed to do this. You change conf level to 0.95, or even better, you don't have to do anything. You just delete this option and just run this code, because by default, computer will think you are wanting a 95 confidence interval. So if you run this line, it will generate a 95% confidence interval automatically. However, if you want to calculate this by hand, you have to change this A accordingly, because previously we want 90% of data in the middle. So in this case, we want 95 in the middle. So on both sides, it has to be 2.5%. So that means the quantile has to be changed accordingly. You have to recalculate the critical value A because we want a different quantile. In this case, it is 0.975 quantile, but everything else stays the same. The standard error does not change because we are still dealing with the same sample. The mean doesn't change. We rerun these two lines of code with a new A. This is it. So the left boundary is 20.88 and the right one is 42.56. And if you'd like to compare this with the one auto-generated by computer, as you can see here, the result is identical. Well, in the last part, you are supposed to give interpretation of this confidence interval. Well, this is what you can see. Basically, you are 95% confident that the true value of population mean will be in between 20.88 and 42.56. Okay, 6.3.5. The first part, or the part A, is exactly the same with previous two questions, so I'm not going to repeat myself. I'll just go ahead and say you can use either of these two options. You can do this by hand with a calculator, or you can do it in R. But if you decide to do it in R, make sure you copy and paste the corresponding code clearly into your homework document. The second part question is really interesting. It asks you, like, will 95 confidence interval cover 95 of the data in your sample? The answer is obviously no, because if you are actually looking at any confidence interval, especially their formula, the center, which is y bar plus or minus constant A, which we've just found out in last three questions, by using a quantile function multiplied by the standard error of y bar. So the standard error of y bar is actually given by the sample standard deviation divided by the sample mean. So as you can see here, this is pretty obvious, because as long as you are increasing this sample size, this term as a whole is going to be decreasing. And just try to imagine if you have a large enough sample size, this term is going to 0. So the confidence interval will be infinitely narrower than your data. So that means this is not possible, especially when you have a large enough sample size. This question is about a normality assumption. We have to make sure y bar is normally distributed. There are two ways to make this happen. You either have a population distribution that is already normal, or you have large enough sample. In this case, we don't have large enough sample, so we have to make sure that the population distribution is normal already. So the one way to check this is to give a QQ plot. That is what the author means by appropriate graphs. As you can see here, we already have the data ready. We have these two groups. So let's run these 2 lines of code. The next thing, as you can see here, is use a command which is called QQnorm and pass in whatever the data you want to work with. So if we click run, and this is what we can see here. This is a normal QQ plot. What you are looking for is whether you can fit an imaginative 45-degree line on this plane. In this case, obviously you can do that, so we can say our data is still roughly normal. And similarly, we can apply this kind of analysis for the decaf group. So if we run this line of code, we see another QQ plot, and this plot is for the decaf group. And I think we can say the same thing about normality for the decaf group, by which I mean it is still roughly normal because we can fit an imaginative 45 diagonal line on top of this scatter plot. One more thing, if you want to toggle back and forth among these 2 graphics, this is what you can do here. See this little back arrow, click this, you go back, and click this, you go forward. Another thing that I want to point out here is, sometimes you just want to plot them side by side, which makes it a little better. You can set this following option here. This C1, 2 means that you want this graphics to be arranged like 1 row and 2 columns. So if we run these 3 lines of code, as you can see here, we have a side-by-side QQ plot. And if you don't like the ratio of this graph, it's pretty simple in RStudio. You can just drag this to resize like this until you feel happy about what you see. In this question, we are supposed to deal with the 2 sample confidence interval based on the t-procedure. It is basically the same with what happened in 1 sample t-test, but the calculation is going to be way messier, as you will see. So basically, in order to get a 95 confidence interval, this is our template. As we can see here, the center is still y1 bar minus y2 bar and plus or minus some constant multiplied by the standard error. So we have to figure out what is the standard error and what is that critical value. Let's do them one by one. First of all, the critical value that we have to find out is actually the 97.5 percentile, because we want to cut our distribution into 3 parts, and in the middle we got 95%, so on both sides it has to be 2.5%, and that is the reasoning. That critical value is given by QT 0.975 and degrees of freedom is 38, which is given by the textbook. So in that case you got A. But in case you wonder where do we get this 38, this is how we find it. This is actually called the satellite degree freedom, the calculation of which is really messy. But because it's already a given, we don't have to get into the rabbit hole. But the point here is, as long as we have the standard deviation and the sample size of these 2 groups, this is actually something plausible, but it's just really messy. Next up, we want to find out y1 bar minus y2 bar, which is kind of simple. The mean of red minus the mean of green. This gives you y1 bar minus y2 bar. Lastly, we have to find out the standard error of these 2 groups, and here is the formula you want to follow. So as you can see here, we want to get the standard error of the first group and second group and do some manipulation so we can get standard error of these 2 groups. And by the way, because the standard error, you square it, you got variance, so we can use sample variance directly without squaring the standard deviation, which is really awkward. So lastly, we have to assemble everything together that we just got. In order to have the left boundary, we have to use y1 bar minus y2 bar, subtract the multiplier A, which is the critical value, multiplied by standard error. And on the right hand, we just have to change this negative sign to a positive one. So as we can see here, the left bound of this 95 confidence interval of mu1 minus mu2 is negative 1.61, and the right hand, or the right boundary of this confidence interval, is 0.45. However, if you think this is too much work, actually we can use some built-in function in R and we can solve everything just by 1 line. The command is still t-test. We have to pass in more than 1 variable in this case because we have 2 groups. So let's pass in 2 arguments. The first group and the second group, because this is a 95% confidence interval that we are dealing with, so we don't have to specify that confidence level whatsoever because that is a default value. So if we run this line, we got the 95 confidence interval. We can compare what we got here with what we got here, which is exactly the same. The last two questions are mostly about hypothesis test. Part A and Part C of question 7.2.3 is really representative, so I will only focus on talking about these two questions, and everything else is just a repetition. Part A, if you want to get a conclusion based on p-value, you just need to compare p-value with alpha. If your p-value is small enough, which means smaller than alpha, you can reject the null hypothesis. If your p-value is 0.065, which is bigger than the threshold 0.05, then you have to say you fail to reject the null hypothesis, or you have to accept the null hypothesis. And part C is about find p-value based on t-statistic. This is the idea of how to do it. So for instance, if we observe 3.75 in this case for a t-distribution, so by definition, the p-value is a probability of finding something that is even more extreme. So that means actually you have to find out the probability of this shaded area. But that's not the end of the story, because by more extreme, you can also referring to the smaller side. You know, it can be like crazily small. So we have to also take care of this side, because this whole thing is symmetric around 0, so this is negative 3.75. So you have to also take care of this area. That is the p-value. Again, p-value is a probability of seeing much more discrepancy than what you have observed. So if we calculate the p-value based on this paradigm, this is what we will have. See, on the left-hand side, you want to calculate the probability of a t-distribution that is smaller than negative 3.75, and the degree of freedom of this distribution is 19. So that gives you the probability of this part. And next, we also want this part, but remember, we can only calculate smaller than probability. So in this case, we have to calculate this bigger area and use 1 subtract this bigger area. So this bigger area is given by pt 3.75. The degree of freedom is 19, and we have to use 1 minus. So lastly, we want to add up these two probabilities, this part and this part. If we run this line of code, the result is 0.001. The next thing we want to do is we have to compare this thing with the alpha level, which is obviously this one is smaller than 0.01. So we can reject the null hypothesis based on this p-value. And here is another trick. Actually, this thing and this thing is symmetric around 0, so they have the same area. So actually, we only have to calculate one of them. For instance, if we just calculate this one and multiply by 2, we can get exactly the same result with this one. So let's run this. See, we can get the same probability by just calculating one side and then double it.